Okay, hi guys. Welcome to this crazy introduction to category theory. This is going to be not me talking for 90 minutes, hopefully. So this is going to be fun. We are going to learn a lot of things, and hopefully we are also going to write some code. So I'm going to talk a little bit at the beginning to give you the opportunity, if you can and if you're willing to download the code and following what we are going to do from your laptop. So no matter what I do, go to that link, download the code, and hope that the internet is not going to break. There is one dependency only. There is SBT to download, but hopefully it's going to be fine. Yeah? So ready for this crazy adventure that is going to last 90 minutes? Yes, we are. Awesome. So what are we going to do? So this is the aimed agenda. We don't have to do all of that. So we have all the time to stop, talk about it, and reason about things. But the idea is that if everything goes as planned, we should have a mini implementation of our category theory library. So we're going to implement everything from scratch, and hopefully it's going to work. Yeah, sounds good? So we are going to talk a little bit about what category is, why we should matter, why it matters for us, and then we are going to describe in a non-mathematical way. So I do apologize if any mathematician is in the room. What a monoid is, we are going to implement it, functor, applicative, and monad. Sounds good? Awesome. So first of all, why am I talking about this? The reason why I'm talking about this is because when I started my career, I was a Java developer. And at uni, no one ever mentioned the word monoid or monad to me, right? I knew about the observer pattern, factory patterns, you name it, I knew it, all about it. But when I started doing Scala, suddenly I realized that a huge chunk of my background was outdated. It wasn't cool anymore, right? So I found myself wondering, I wish I knew more math because it would make my life a little bit better. And what I mean by that is that I found myself many times in a situation where I was attending the talk, and I could feel that what they were talking about was awesome, right? But then at the end of the day, it was a disaster because I couldn't get it, right? So, for example, yesterday, semi-direct product. I have no idea what it is. I looked at the formula. I still don't have a clue of what it is. I'm going to watch the talk again at home, and I will look again, and I will still not get it. And then probably at the fourth or fifth time, I will get it, and I will understand why it's so cool. So my brain is not used to reason with mathematical formulas. That means that all these new functional programming things that I had to learn, it took me a while. But hey guys, I'm telling you, it's definitely worth it, the pain, because then everything is awesome and everything is like, oh yeah, this is so cool. So stick with me, hopefully we are gonna learn something new in these 90 minutes. So a little disclaimer. You don't need to know category theory to write Scala code, right? Let's make this clear. You can write reasonably good Scala code without knowing anything about category theory, right? You don't even need to know what category theory is to write functional code, right? The principles of functional programming are simple enough, then you don't need to know what a monad is to actually take full advantage of it, okay? So why am I here? Because knowledge is cool. So it will allow you to get a deeper understanding of why the people that write libraries write them in the way they do. So I went away, and it was like, no, I need to understand why everybody's so passionate about all these functors, monads, and I need to understand the why. And then I went away 4 months. Yes, it took me 4 months. I did a little bit of studies, and then life was amazing. Everything made sense, and it was beautiful. So everything starts on how we try to translate the way we reason into code, right? Because that, at the end, that's what programming is all about. We are telling a computer how to do things, right? So for example, this morning, we took a bus to come here, right? So we found where the bus station was. We walked there, then we found the bus. We went on top of it, and then we stood there for a while until, the driver said, OK, we are there, and we went off the bus, right? So our reasoning was about composing simple steps, right? But when we thought about how we are going to get there, we didn't thought about, OK, I'm going to move my left foot, then I'm going to move my right foot, then I'm going to contract my muscles that are still hurting from the hiking to move, right? When we reason, we tend to split our tasks in smaller tasks, but a lot of details are left behind. So our brain is basically tends to reason into composition of simpler tasks and abstraction. Things that are not important, that we know how to do, can be left out, right? And this is reflected in, I would say, probably any programming style we have. So for example, in object-oriented programming, we compose objects, not in a mathematical way, but we structure our programs in objects. And the abstraction is around how each object behaves, right? We know what it does, but we don't know how it does it. Functional programming, on the other side, is about functions that compose together and then have the abstractions are over some mathematical laws, right? So, and this is where category theory comes in, because category theory is the study of how things compose. I'm not saying types, I'm not saying functions, I'm saying things intentionally. Because it turns out that what you compose is not important. What's important is how you compose it. Yeah? Everybody with me so far? Cool. So for that reason, I don't like category theory, it's too mathematical. I'm going to call it arrow theory, because at the end of the day, all we are going to do is that we are going to talk about arrows. And I'm going to explain in a second what an arrow is. OK? Cool. So hopefully you are starting to compile the code. So let's start with what is a category. So a category is a group of two things, objects, where objects are not clear what they are. It could be shapes, it could be types, it could be chairs, it could be anything really. But the important bit is that these objects are connected by an arrow. An arrow is something that has a clear direction. That's it. So category is objects and a well-directed arrow, right? Obviously, we are not mathematicians, right? So when we look at this, we immediately think at our category. Our category is usually about objects being types and arrows being functions. But from a mathematical point of view, they have to solve a lot of other problems that we don't have, because they don't have a clear definition of what these things are, right? And this is when it gets really interesting, right? So now we start playing their game, right? So we know what a category is, but a category is not just an arrow. We have some rules in our game. So the first rule is called composition law, and I promise there's going to be a few weird letters, and then we will forget all the letters. Composition law, in human terms, it means that if there is an F, meaning an arrow that goes from A to B, and if there is a G, meaning an arrow that goes to B to C, then I know it's in my rule books that I can create a new arrow that is made by composing G after F. Mathematicians are weird, so for some reason they like to to write things the opposite way. So as a programmer, I will say F and then G, but they do G after F. So that little O symbol means after. You get used to it after a while. That's the official annotation, but basically means do F first and then apply G. Other rule, extremely important, we are going to see it all over the place, is the identity rule. It basically means that you have a useless row that goes nowhere. It just points where you already are. So by taking that row, if you think of this like a little bit of a graph, you basically go nowhere. So if you are in A, and if you are in B, and you take identity of B, and then, if you're in A and you take identity of A, and then you take F, you still end up in B, even if you just go from A to B directly using F without going through the identity. So the identity basically doesn't change anything, okay? And finally, this way, this rule of composition must be associative. What associative means, it's just we don't care about the order, right? We have better things to think about, so we don't care about the order, forget about the order, right? So it doesn't matter where we put our parentheses when we travel through our graph. Basically, what that formula means is that the green path is the same as the black one. And the reason why it's there is simply because we cannot be bothered to think about implication of applying operations in a particular order. Yeah? So we are going to see these rules every time we are going to talk about monoids, applicative functors, and so on and so forth. And they're really important to remember. So identity, a row that does nothing. Composition, the ability of adding new rows by composing existing rows. And the associativity is, I don't care about the order of my operations, yeah? Everybody with me so far? Cool. But what do we care, right? We like code. We don't like all this mathematical jibber-jabber, right? So that's a practical example of what a category is for a programmer, right? So for example, we could have the set of all the strings. And we could have a function that is called size that goes from the set of all the strings to the set of all the ints. And then we have another function that is bigger than 2 that translates the set of all the integers into a Boolean. We know that it's possible to define a function that it will not change my string. For example, if we concatenate our string to the empty string, we know that the string is going to stay the same, right? And we also know that we can compose the function size and the function bigger than 2 and create a new function that is called size bigger than 2. We do that all the time, right? So it's nothing crazy. All with me so far? Okay, cool. So out of curiosity, how many people managed to compile the code? Okay, good, good. How many people saw the secret message? You're ready to rock? Okay, cool, less people, but it's going to be fine. It's going to be fine. We're going to use my laptop, and you are going to tell me what to write. Okay, so let's start talking about more interesting things, right? We understood that this category theory is something that we actually use every day at work. We just didn't realize. But let's start thinking simple, right? What is the simplest category that you can think of, right? A graph, if you think at a category like a little bit of a graph, for me, the simplest graph that you can think of is when you just have one object, right? So let's recap our rules. Identity rule. we know that if this graph is a category, we need to have an arrow that basically does nothing. There you go, identity is there. And also we know that by combining two arrows together, we can create new arrows, yeah? So this looks like a valid category to me. Any objections to that? Okay, cool. So mathematicians call this monoid. Mono means one. And again, it has exactly the same rules that we have seen so far. Don't focus too much on the formulas. The formulas are just things that you write a test on, and then you use them to check that your implementation is valid. But again, to go through a practical example, this is, for example, a monoid for the integers, right? So imagine the set of all the int, and then imagine that the arrows are the single elements of the set int. So we have the identity, and we have a composition. So if composing two arrows means adding them together, then the identity is going to be 0. Okay? But enough with theory, let's do some coding, right? So what we have seen here is basically that we need to define two things, right? We need to define what is the identity and what does it mean to compose two arrows together, yeah? And how do we do that with Scala? Type classes all over the place. We will play a lot with type classes today. So there you go. That is actually exactly the same of what we have in cats. It's the definition of what a monoid is. Okay? So you have an identity that returns an element A, and then you have a function compose that is somehow smashing the two things together. Okay, let's do some coding. So I believe that the best way of understanding things is actually by trying to do things with them. So what we are going to do now is that we are going to try to define a monoid for int and the monoid for string. So what I'm going to do now is I'm going to take my IntelliJ, sorry, Sam, screen up, and we are going to try to code these together, yeah? Cool. Okay, I can do the trick. So, for those of you that didn't manage to download the code, I'll show you in a sec. So, this is an extremely simple project in Scala. As you can see from the SBT file, it has no dependencies apart from Scala check. The reason why it has some, the Scala check has dependencies because we still need to respect the mathematician rules. What I've decided to do is basically, I don't want to bore you guys with all these mathematical formulas. I'm just going to translate those formulas into Scala check tests. So we already have the tests. So they're going to make sure that we play by their rules, yeah? And then we have the definition of what a monoid is. Okay? So now we have this beautiful task. We have an object that is called monoid instances. And we are required to implement an instance of monoid of int and an instance of monoid for string. So are we ready to start? Yes. So any ideas? Okay, I'll break the ice by saying, for sure, we need to implement the type class. And then we have to write something here. what kind of monoid do we want to implement? Because, you know, there could be probably more than one monoid for int. We could do with the sum, yes. So if we go for the sum, how would the compose be? Compose will simply be x plus y, right? And the identity, we know that the identity for sum is 0. We could also do something a little bit different, right? We could go for multiplication, and then the identity would not be 0 anymore, will be 1, yeah? And for string, one easy option is to just write a monoid for the string composition. So compose will be simply the string interpolation for x and y, and the identity will be the empty string. Yeah? Cool, but never trust me, always run the tests. So, view exec mode, good. So if we compile this, so everybody can see, yeah? SBT. Run. Ready to rock. Awesome. So that means that we can write test only monoid Yay! Awesome. So Scala check, what it did is that it randomly generated some numbers. He tried the monoid for us, and he made sure that the rules of a monoid are still respected. Rules, what are our rules of the game? Again, identity, composition, associativity. Yeah, all good with me so far? So what is a monoid? It's simply something that generates elements of a set. Nothing else. Cool. Back to our presentation. Let's do something a little bit more interesting, right? Most of us know already what a monoid is. So let's assume, you know, now that we have seen what a category with one object is, we want to do a little bit more. So let's assume that we have a category with more than one object, right? So for example, we have this beautiful category with a flower and a triangle, right? And what can we do with it, right? Well, something that we could do with it is, for example, we could copy this category. How would you copy this category? Well, the object will be the same, but they will be like put in a new context, like put it in a box. And the arrows will be the same, because the arrows are what really matter, right? So we cannot really change the arrows. So does that ring any bell? They should. So basically what we are doing now, again, is that we are copying the objects are the same, we're just putting them in a box, and then all the errors are copied over, right? So basically what we are saying is that the information that is encoded in the category is the same. I'm just adding some extra type of information, a little bit like metadata. So believe it or not, we do this in Scala all the time. So for example, we could have a box that is called option. That means, hey, by the way, be careful. That thing might or might not be there, right? So we need to know that we need to be careful when we access it. And it also means that if we know how to transform a flower into a triangle, then we know how to transform a flower that is in a box into a box containing a triangle, right? We do this all the time, and it's all over the place. Can you think of any other example we have in Scala, Sorry? It is actually the definition of a map, but basically we, for example, have lists. A list could be seen as a box that contains multiple instances of the same object, or we have try, that it's a box that could explode in our hands any moment, or future, that it's a box that is going to take some time to be filled up with whatever is containing, right? So this way of reasoning, we have the content of the box, but we also have the context on which we are producing our data. And that is extremely useful. So we do this all the time in Scala, and the way mathematicians call this, they don't call it category in a box, because they don't like that. They call it functor. So as the gentleman in the audience was saying, this is exactly the concept of a map in category theory. Again, same rules as before. This is still a category, so we still need to have an identity to be able to create new arrows by composing existing ones, and we don't care about the order. So we spoke about this. So basically, what do we need to implement this, right? So we said we have two operations to do. The first one is to copy exactly the same objects, but put them in a box. That is kind of a type constructor, right? We are wrapping things into a box. And then we basically have to create a new function that goes from a box with a flower to a box with a triangle by combining the existing arrow in the other category. Yeah? So basically, we need a function that it tells us how to mutate the content of a box. And that is basically a functor. Yeah? So let's do some coding. So what we are going to do now is that I have created a couple of weird data structures simply because I wanted to make sure that you guys were tempted to use any particular Scala collection function. All I've done is that I've divided some ADTs, maybe and 0 or more, that basically represent the structure of an option and a structure of a list. And we are going to define a functor for it, yeah? Cool. So let's go and change. Let's see a little bit what we have. OK, so presentation mode. Awesome, everybody can see? Yes, OK. So first of all, definition of maybe is basically the same of an option. So a maybe is a CL abstract class that has two possible implementations. You could have a just that contains a value, or you could have an empty. And how do we see this in our box analogy is that you could have a box that contains something, or you could have a box that contains nothing. Yeah? On the other side, we have another ADT, 0 or more, that has two possible status. The first one, it's a box that contains 0 elements. And then the second one, it's a box that contains at least 1 element. Yeah? So we are pretty familiar with this. This is normal code for us. And also what I've done, we are going to see if we get to monads, I have defined an operation append that is simply checking if we reach the tail of our data structure, and if we reach the tail, it's going to append the other data structure to it. Yeah? All good? Cool. Okay. So this is the definition of functor that we have seen in the slides. It's fairly simple. You give me a box that contains an A. You give me a function that will transform my A into a B, and I will figure out how to do this. Yeah? Okay, let's do some coding. Okay, same as before, type classes all over the place. So, new functor maybe. So, any ideas on how we could implement this? I'll give you a little hint. Pattern matching. Pattern matching is our friend. Match case just A, and then we will write something, or case empty, and then we will do something else. So if we have a box that contains just one element, well, it's easy, right? We have the function. So what we do is that we say, keep the box, and just apply the function to whatever this box is containing. And if we have nothing in the box, well, I'm sorry, there is nothing I can do, so we just return empty. Yeah? What about list? Or let's call it with the proper name, 0 or more, right? We are still going to do pattern matching, right? So box of A can be into statuses, right? It could either be 1 or more, meaning being at least one element, and then we will see. Or it could be a box that is already empty. So what happens again if my box is empty? Well, there isn't really much I can do with it. And what if I have multiple elements in my box? Well, what I could do is that I could say, well, apply my function to the head of the first element that you find in my box, and then recursively go and do the same with the all other elements. Yes? Does it make sense? Cool. Congratulations, you just implemented a functor in cats. Okay, never trust me. Always run the tests. So if we do test only functors, time. Yay, awesome. So thank God Scala check exists, we still respect all the rules of our game. Yeah? Cool. Okay, let's step up a little bit and do something a little bit more difficult. Oops. Yes. Okay, so we got this idea of having boxes and being able to reason around what these boxes might or may not contain. But can we combine boxes together, right? So boxes can contain anything, right? They can contain even a function. So let's assume that I have a function in a box that goes from A to B, and then I don't have an A. I have a box of A. And remember, all we can do so far is just mutate the content of a box, so we cannot get rid of any box, right? And the result that we want to get out of it is we want to get a B. So what do we need to do now in order to achieve this? Well, we need to be able to open all the boxes, combine them together, and then put the result in a new box. Right? So it's not as simple as before anymore. We are adding more and more power to our box. And this idea of opening lots of independent boxes and trying to smash them together, mathematicians call that applicative. It's a scary word, I know. It took me a year to get used to it, but it's not so bad if you think about it. And there are lots of rules around applicatives, but the key idea that I want you guys to focus on is that we still have an identity, we still have a composition, we still have associativity. Okay? So again, the thing that now we have to express with our type class is that we need to be able to create a new box, because that's the box that is going to contain the result of all the previous boxes. And we need to know how to open a box so that we can smash all the content together. Yeah? And this translates in basically this type class. So pure is the idea of, I have this content, put it in a box. AP is basically the idea of, I have all these boxes, open all of them, and somehow combine them together. Yeah? Spoiler alert, turns out that we can still, this box is a lot more powerful than what we have seen so far. So it turns out that this is still a box with a map defined on it. So by using pure and AP, we can redefine map. It means that every applicative is also a functor. Yeah? Spoiler alert, because we are going to do it. It's going to be fun. And obviously, you know, this is applicable to, there is no limit on how many boxes we can open, right? So if we need 2 boxes to satisfy and apply our function, then we will have a function that, that does that. And we can go up to 22 values. Okay? So what we are going to do now is that we are, first of all, going to define map in terms of AP and pure. And then we are going to define an applicative for maybe and an applicative for 0 or more. Okay? Cool. So okay. So this is our this is the type class that we have in the code that defines what an applicative is. So the first step is to implement map in terms of pure and AP. So this is what I love about Scala, that sometimes all you need to do is look at the types and try a way to put them together and make the compiler happy. And once the compiler happy, it's going to magically work. So any idea on how to do that? Pure half. You have a winner in the audience. Awesome. Whoops. So pure is basically going to create a new box. That's something that we definitely need to do, but it's not the only thing that we need to do. We still need to apply an A to the function, because at the end of the day, we want a B, right? And in order to do that, well, we can just use AP, right? So we can say this. Let me write it first. Okay, so IntelliJ is happy. Doesn't mean that the compiler is happy, but that's a good sign. So what we have done here is that we said, okay, we have AP that takes a box that contains a function. So map is basically wrapping the function into a box, and then it's basically the same. Okay? Cool. The second task that we have is to implement an applicative for maybe and 0 or more. So as usual, type class is all over the place. So we have to define a pure function for applicative maybe. So we said that pure is simply putting things in a box. So what is pure going to be? Exactly, it's going to be just A. Simple, right? And for AP, things are going to be a little bit more complicated. But again, we have a friend, and our friend is called pattern matching. Well, basically what we need to do is, if both the boxes contain something, then yes, we can do it, right? We can extract the content, combine them together, and then put it in a box. If any of the boxes is empty, sorry, bro, nothing I can do. So what we could do, this is just one implementation, we could use pattern matching, and we could say, well, if they both contain something, so if the first one contains a function and the second one contains a value, what I could do is that I could apply the function and then put it in pure. Does that make sense? Cool. Well, if any of the boxes of both of the boxes are empty, well, I'm sorry, nothing I can do there. So that is empty. Cool. And now the interesting bit. What about 0 or more? The reasoning is going to be similar, but not quite. Okay, pure. Any ideas for pure? We're just going to put it in one or more representation of our box. So that will be one or more A and then empty. So it's basically, it's going to be 0. It's basically going to be a box that contains exactly one element. And for AP, same as before, we have to pattern match. So box of A, and then match, and then case. So if both the elements contains at least one thing, then yeah, probably we can make it. So there will be HF. I'm checking the solution. Okay, yes. So what can we do here? Well, you probably realize that this doesn't really quite work. The way I managed to figure out that this doesn't work is that you have, on one side you have a list of a lot of functions, And on the other side, you have a list of a lot of parameters. So how can you map them together? What we should do is to create a zip operation so that we know that we can apply the first function to the first parameter, and so on and so forth. So applicative for lists is not so simple to do. Other things that we could do is, for example, we could just say, and that is actually my implementation, it's a little bit silly, but we just apply the first function. I'll show you in a second what I mean.
Why do you need zip to be able to apply elements as they go? Can you not just call yourself again?
So why do you need zip? Could you just call yourself again? That's another possible implementation. Yes, absolutely. But the idea is that there isn't an easy way of solving this with lists. You need to define a structure, a strategy for it. Okay, I'm gonna quickly copy my solution so that you guys can fully understand what I mean by that. Okay. Okay, so I think now the problem with this implementation will be a little bit clear. The problem is that underscore over there, one or more HF underscore. So basically, while we iterate through the second box, we don't iterate through the first one. So we will always apply only the first function to all the parameters of the second box. And that doesn't really work. One solution will be to apply all the parameters to all the functions. Or another solution will be make sure that by zipping them together, that you have the same number of functions with the same numbers of parameters. So this is is an implementation details that, you know, when people create a library, they are going to decide how to do it. The mathematical laws don't tell us how to solve this problem. In fact, even though if this implementation is completely wrong, I can show you that if I run my test will pass. In fact, I realized this just this morning, and I didn't have the time to fix it. I told you live coding always go wrong. But it's fine, we're here, we're alive. So, what if I run my tests? Now you guys will see that hopefully the test will pass. So this is as you can see, we I'll show you a test in a second, but we are running lots of tests because we still want to make sure that our implementation of an applicative still respects all the rules of functors. But this is a demonstration of the fact that although mathematical laws help, we still need to think about what we are doing and make sure that the way we are performing our operation makes sense according to our contents. Okay. So the way we run tests is actually quite interesting. So presentation mode. Oh, it's already on. That's good. So the only thing that I want you guys to pay attention to is this line. So all the properties of an applicative they still have to respect all the properties of a functor. So the bit that I would like you guys to take from this presentation is Although sometimes there are a lot of mathematical rules that don't make much sense, we can still find a way to translate those into code and make sure that our code respects those rules even if we don't fully understand them. Yeah? Good. Okay. Back to our presentation. And we are now at the last bit of our presentation. Okay. So the last bit of our presentation, right? So far we have seen what is a category with one object, how we can map a category into another category. But we still have a problem, right? What if somehow I have a box that contains a box, right? So for example, this could happen, right? That you have a box, you mutate its content, and by mutating the content of this box, you get another box back. So far, we don't really know how to solve this problem, meaning how to squeeze two boxes together, right? All we can do so far is mutate the content, move the content to a new box, and how to combine the content of several boxes together. But we don't have a way of getting rid of a box. So far, all we have done is the box, the context of our data was always there. And that's where the idea of monad comes in. So a monad is simply something that smashes boxes together. So if you are a mathematician, I do apologize. So monadic rules, again, nothing new. It's identity and associativity. I didn't put the formulas there because I was scared of them. So let's move to the implementation, right? So all we need to do, again, is just to write a function that if I have two boxes, is going to get rid of one of them. And that, in terms of Scala code, it's flatten. And turns out that this operation of getting rid of a box is so common that it's possible to write another really useful function that is called flatMap, that is just a combination of map and then flatMap. Yeah? So a monad is a functor, just more powerful. And why people are so passionate about monads. The reason why they are so useful for us programmers is because it basically means that we can chain operation together. So what we have seen with applicatives so far is that we were combining independent boxes together. But life is not perfect, right? Things are rarely independent from each other, right? What happens if all these side effects that you have depend on it? So monad is the answer. So for example, you could have a way of producing from a box of A to a box of B, and by getting rid of boxes, you can change all their operation, combine them together, and find a way to produce a box of A into a box of D. Yeah? And again, we do this all the time. We just don't realize. We use the for comprehension that is just syntactic sugar, but is exactly the same. Okay. But turns out, and the Haskell people took a while to figure out this, that a monad is even more powerful than what we expected. So if we shuffle things around a little bit, turns out that we can write a monad in terms of an applicative. And what that means is that instead of thinking of getting rid of two boxes, we can just define flat map and pure, and all the other functions that we need will come as a consequence to that. Okay, so every monad can be implemented as an applicative. In human term, what it means that every operation that is dependent can be seen as independent, right? Being dependent is something stronger than being independent. Mind-blowing moment. It took me a while, but it's quite interesting. And that is exactly what we are going to do. So really quickly, we are going to define flatten in terms of flat map. We're going to define map. And we are going to define AP. OK? So back to some coding. OK. So, whoops, presentation mode. Everybody can see, yeah? So again, mathematical laws are important, but at the end of the day, for us, it's just important that we can translate them into a test. So this is the test that we have written that makes sure that whatever implementation of a monad we will do, it will follow the mathematical rules. And then let's go to the type class. So we know that we can implement flatten in terms of flat map. Okay. Any idea how to do that? Okay. One way of doing that could be by using flat map and then the identity function. So if we do flat map, I'm just going to cheat and look at my solution, box of F, and then we can explain all the types. Box of X of A, and then identity. Okay. So does it make sense? It's basically just, again, trying to fit all the types together. So by using flat map, you basically, by the definition of flat map that you will get rid of a map. But the problem with flat map is that you need to pass a function. Easy. Just let's pass a function that does nothing. Identity. Problem solved. Okay. What about let's do AP. I'll look it up. So that will be flat map. And then will be box of A, and then will be a function. Oops, what's going on there? Ooh, type in Feral. Bad Scala. Bad IntelliJ as well. What's going on? Flip marks. Oh, it's me, guys. It's me, guys. Okay, now it makes sense. Nope. So, let's think about this, right? The first parameter is going to be a box of A, right? And then the second parameter, according to the definition of flat map, it needs to be a function that goes from A to box of B. So it means that, oh, come on. Maybe IntelliJ doesn't like me. You see, that's exactly why you should use Enzyme. So the code was right. It was just IntelliJ that didn't like me. Okay, sorry guys. Panic moment, like in every live coding demonstration. Okay, cool. So it kind of makes sense. So, well, yeah. Okay, let's go through map. And map is just going to be a flat map of box of A, and then we're just going to box our function. Okay? So this is just error and trial. Keep going till the compiler will be happy. But the idea is that so far, we have defined every functions in terms of flat map, pure, and that's it. OK, cool. So last bit is going to try to actually do something with this code. So we are going to implement a monad for maybe. Well, pure, we have done that already, right? So we are just going to cheat and say, give me the same implementation that I've done for the applicative in the previous exercise. And we are going to do the same for 0 more. So it's going to be the 0 applicative pure of A, right? We already figured out what that means. The only thing that we need to figure out now is what actually flat map is, right? And again, pattern matching here is the solution. So box of A match. Okay, so again, we have 2 possible statuses for our box of A, and that is just A, and then we will think about what to do, and then empty, and we'll think about what to do. Right. So if I have a box that contains an A, what I could do is just take whatever the box is containing and just apply it to the function. So there will be f of A, right? And if one of the boxes is empty, there is nothing I can use to apply my function. So in that case, it will just be empty. Yeah? Let's have a look at 0 more. Again, pattern matching for the win. So we have 2 possible statuses for 0 more, 1 or more that it could contain an element. And we will see what to do. And another stage that is called 0. OK, so if I have a box that contains something, again, we are fitting the types here. We apply the function to the head. And then what we have to do is continue to iterate until I reach the end of my ADT. So for that, we have the beautiful append function that is going to say keep using the flat map operation for over the tail using the function f. Yeah? And again, if there is nothing I can use in my function, then there's nothing for me to do. Yeah? Cool, let's run the tests. Yay, lots and lots of tests. So apparently the mathematical laws are still respected. Yeah? Cool, that was the last bit of code. So we have seen that at the end of the day, we don't need a powerful language to implement something that respects the laws of category theory. All we need really is just an expressive type system. So let's go back to the presentation. Okay, so hopefully I managed to give you some intuition on how they managed to came up with all these really nice implementations. But I want to leave you guys with the final intuition. So I've been hearing that sentence for about 3 years now. Monad is a monad in the category of endofunctors. There are a lot of words that are not clear what they are. So hopefully we are now able to kind of understand what this sentence means. So the first word that is a little bit problematic is endofunctors. What the hell is an endofunctors? So it turns out that it just means that when you map a category, you're still in the same category. So it's basically the same of functors. In programming, we always use endofunctors. It just means that you have a map function. And what monoid means, we have seen that monoid means two things. You have an arrow that does nothing, and you are able to compose things together. So that means that you have a pure function, a flatten function, and a map. Having those operations is exactly the definition of what a monad is. Hopefully that will give you some intuition why people are so passionate about this sentence. Monad is a monoid, means that has a pure and a flatten in the category of endofunctors. It means that has a map. So sometimes, the expression is really complex, but what it means is actually fairly easy once you get your hand around it. Okay, so it was a fairly long journey, a little bit painful, a lot of content, but these are the key things that I would like you to keep in mind after attending this presentation. Category theory, why it's so important to us is because it's a mathematical description of how things should compose. And what is a monoid? It's just a category with one object. And when we copy one category into another, meaning we have a map function, that's a functor. When we have a lot of effects, and these effects are independent, so it doesn't matter the order in which we apply them, then we have an applicative, meaning we have a pure and we have an AP. And when we have effects that depend on each other, so the order does matter, then we have a monad that has an extra operation that is flattened. Okay? So we kind of try to implement our own version of a category theory library. We obviously haven't covered, not even close, everything there is to know about category theory. This is from Robert Norris. Is a mapping of all the type classes that we have in cats. So I cannot read it, but the idea that I want to give you is that there is a lot out there that we still don't know, and the future is it's interesting because every day people are implementing new mathematical principles into coding. So hopefully we will understand some of it, and we can use it in our code. But again, the important bit is that sometimes it's not important what you're composing, it's important how you are composing it. So this was a little bit of the result of all my studies in these months. And these are the sources that I used in my studying. So if you want to know more about category theory, I know that today's lecture was quite tough. But if you want to know more, spend some time on it. I strongly encourage you to do that because it's going to give you a better understanding on why we write the code the way we do. So we have a really good presentation from Philip Walden on why category theory matters. And then there are a series of videos from Barthold's on category theory. If you want to know more about how this has been translating into code, CAT's documentation is a good starting point. We also have the representation of all the type classes that we have in Scala. And then finally, have a look at the code. If you want, grab me for questions. I'm going to be around. That's my Twitter handle. If you want to insult me, you can do that on Twitter. Okay, thank you, guys. Do we have any questions? Yes?
Do you have your slides available?
Sorry?
Are your slides available?
My slides and all the code is going to be available. I'm going to tweet on it in 10 minutes. So they are going to be available to go through it again. Awesome. Any other questions? Yes, please.
Let's say that you want to record an infinite stream with the junction monolith for the stuff. As soon as there is a true, then you need another tag class for monolith that you have a code line name for a second parameter, so you need to stop. So it's kind of a problem in Scala. How do you, what's I know that in Scala the second parameter monolith is by name, cat is string. How do you decide what the trade-off this design is?
I'm going to try to summarize the questions. In specific, for example, string problems, how do you decide when to use this type of coding styling rather than maybe other approaches? And my answer to that is that readability at the end of the day is key. So if you can manage to define a monoid that allows you to produce the result that you want, and the implementation of the monoid is reasonably understandable, I will definitely go through with it, simply because you know that you have some mathematical laws that will kind of guarantee that you're probably doing the right thing. Was that your question? Does that answer your question at all? Okay, so the definition of monoid that I showed, it doesn't work with infinite streams. Yes, you are right. Probably, yeah, we could have a better implementation of what a monoid is.
That's the definition of monoid.
Is the definition of monoid.
Yeah, so Scala Z has by name on the Y, whereas cats in this definition are eagerly evaluated.
I'm not an expert on cats, but as far as I remember, I think it's eagerly evaluated.
Here, so the Y, it must exist before you call this, whereas Scala Z, it's by name. So it can be a func that can be calculated later. So you can, it works for infinite streams or infinite data structures.
Okay, so
It avoids doing computations that you don't need.
okay, I'm gonna sum up for the video is basically that this implementation requires the element to exist, while in Scala Z, you basically have a pointer to the value. So for example, in infinite streams, Scala Z will be able to handle this. Yes, you're absolutely right. I'm not sure about the cat's implementation. I think it's like that.
Yeah, it's exactly.
So yeah, absolutely. There are limitations that are due to the implementation. But hey, the good news is that we can change code, right? So yeah, absolutely. Really good point. Any other questions? No? Okay, thank you very much, guys.